Howdy guys, we're here to talk about mass stoichiometry, all right? So let's walk you right on through it, and let's take a look at example number 10. Now you should remember stoichiometry from last year, and not much has changed. So example 10, we want to calculate the mass of CO2 produced from the complete combustion of 1.00 grams of C2H2. We've got our equation right here, and move my head over to the side. And so we'll definitely start with what we know, right? And we know the mass of C2H2, that's 1 gram, and we're trying to figure out the mass of this one, right? So we can do that using that mole ratio kind of thing. So what we're going to do is we're going to convert our mass of what we know into moles. So convert grams into moles. Remember, just divide by the molar mass. And then we're going to apply the mole ratio. Now this mole ratio comes from the equation right here, moles to moles. For every 2 moles of C2H2, there are 4 moles of CO2. That you get those from the equation. And then we can convert moles of CO2 into grams of CO2. And then we'll find our answer. Pretty simple. So just to review, that this one is given in the problem. That first term, that's always what you start with. The second one comes from the periodic table. Remember, G stands for go to the periodic table, right? And then the third one comes from the mole ratio, and that comes from the chemical equation. And then the last one comes from the periodic table again. Remember, it's got a G in it, so you go to the periodic table. Some pre-AP students keep getting this backwards, but this should be old hat to you, and it should be okay. So for example number 11, pretty much the same. Calculate the minimum mass of iron 3 oxide needed to produce 800 grams of iron. So the absolute minimum mass, this is just a normal stoichiometry problem. If we want to make 800 grams of iron, how much of this stuff do we need? So we'll start with this, and we'll go ahead and do our calculations. We have 800 grams of iron divided by the molar mass. We'll use the mole ratio again. Sometimes the laser pointers use the mole ratio again, and then we'll convert from moles to grams, and we get our answer. Piece of cake. Now, it said 800 grams, and in your notes it says 800, so that has 1 sig fig in it. I don't think the IB test would really put you in the situation where you'd have only 1 sig fig, but I would round to 3, and I would call that on my answer. And I would put the squiggly line in front of it just to show that you know what you're talking about. They don't really care about sig figs. So now, this might be something that you need a refresher on, is the limiting and excess reactants. So I will have to shrink my head and move it over a little bit. Hopefully you can still see my head. It's a little off my screen. A reaction vessel is filled with 4.04 grams of hydrogen gas and 16.00 grams of oxygen gas, and the mixture is exploded to form water. Identify the limiting reagent and deduce the mass of water produced. Well, first things first, you're going to need an equation. That wasn't provided for us, so you'll have to draw it yourself. Well, that might be a point right there. Maybe this is a 4-mark question. That would be the first mark, okay? And it would also have to be balanced. You need to have that 2 and that 2 right there. If you didn't make it balanced, it would screw you up later, and you would also lose that first mark. So, we have about 4 grams of hydrogen, about 16 grams of oxygen. Now remember, oxygen gas and hydrogen gas are diatomic. Remember, so hopefully you put H2 and O2. So now when we have the mass of 2 different reactants, we must find out that it's a limiting reactant problem. This should be a big red flag whenever you have 2 masses right here. So we're going to, now this is the trick that I like to do. There's a couple ways to do this. This is the fastest and easiest way for me, is that I take 4.04 grams of hydrogen, and then I convert it into moles to find the number of moles. And then I do the same thing for the other reactant. I do it for oxygen. So those two reactants that I knew I had 16 and I had 4, and then I converted them into moles. So these are the actual numbers of atoms, if you will. Now what you do is you divide both of them by their coefficient. So I'm going to divide H2 by 2, since its coefficient is 2. And then I'm going to divide O2 by 1, since its coefficient is 1. Now that will give me 1.01, and that will give me 0.5. Now that doesn't tell me much. It doesn't tell me any specific value, but it does tell me that the lesser value is the limiting reactant. Okay, so that is the easiest way for me to do it. You don't have to do full stoichiometry twice. You can just do this instead. All right, and that always works. If you do it, write it all out twice, you notice that the last part is the same, so we're basically omitting that part. Okay, so this is a totally valid way to do that. Now, be careful. Limiting reactant problems show up everywhere. It won't say it's a limiting reactant problem. This example didn't say it. So please, please, please be careful. They will show up in your gases unit, your solutions unit. They will show up thermochemistry. They will show up everywhere. So you always need to clue into the fact that if you have two masses of two different reactants, you are taking that into account. So let's talk about percent yield. Now, IB really wants you to know these things, why that few chemical reactions are completely efficient, where the experimental yield is generally less than the theoretical yield predicted from the equation. And there are a couple of reasons for this. The reaction could have been incomplete. Maybe it didn't go all the way. Maybe there was some kind of equilibrium going on. There are side reactions which are making unwanted substances, or the complete separation of the product from the reaction mixture is impossible. For example, you couldn't dry out your final product enough, and you still got some extra water there, or maybe you have some extra, the purity of your product is not good. The purity of your reactants could also not be good, or the product is lost during transfers of chemicals during the preparation. So those are all big ones for you to know. If they expected you to list 2 or 3, you should know these 3. You would be fine. So the percent yield calculation is very easy. It's just the actual over theoretical yield. Now, this is not in your data booklet, so you'll have to understand this and use it. You'll have to put it in your IA as well to use it as supporting your conclusion. So this is good stuff to use. But that is the efficiency can be put in a quantitative value. So now the actual yield is what you find in the experiment. The theoretical yield is what you calculate in stoichiometry. So let's check through a problem right here. We have aspirin is made by reacting ethanoic anhydride with 2-hydrobenzoic acid, according to the equation here. 13.8 grams of 2-hydrobenzoic acid is reacted with 10.26 grams of ethanoic anhydride. Determine the limiting reagent for this reaction. So they were nice. They told us it was a limiting reactant problem because we had 13 grams of this stuff, and then we had 13 grams of that, 13.8 grams of this. So I'll do the same things I did before. I will find my moles of both of them, and then I will divide by their coefficients, and I will get 2 different numbers. The smallest one, or the smaller one, is going to be the limiting reactant. Okay, easy peasy. So 2-hydrobenzoic acid is going to be my limiting reactant. Now this is the one I'm going to use for my calculations. I'm going to X this out. I do not want this. Forget about it. This is only useful to find the limiting reactant. So now the mass obtained in the experiment was 10.9. We want to calculate the percent yield of the aspirin. So I set up the entire calculation for you, and you get converting grams to moles, and we're figuring out how many grams of aspirin should we have made, possibly have made, and we end up with 15.92 grams. Well, that is my theoretical yield, and this is my actual yield. So I take the actual over theoretical little formula, I multiply by 100, and I get 68.47%. This is a lot easier when you're just watching me on the screen and all the stoichiometry is worked out for you. I highly recommend that after you're done with this video, if you hadn't been taking notes already, go ahead and try to work out the notes problems again now that I've explained them, because that will cement it in your head. If you're just watching this like it's a TV show, you're not going to get much out of it. Okay? Now for this one, for example number 14, we have the ammonia reaction. Nitrogen plus hydrogen makes ammonia. 400 kilograms of nitrogen is mixed with 200 kilograms of hydrogen to produce 220 kilograms of ammonia. Calculate the percent yield of ammonia. This is essentially the same thing. We are, except we have kilograms now, which is not fun. So I'm going to do something. I'm going to say that because 1,000 grams is 1 kilogram, therefore 400 kilograms is 4 times 10 to the 5th grams. Okay? With me so far? So whenever you see me put 4 to the times 10 to the 5th grams, you know what I mean. I have to do that because my molar mass is in grams. If you know a convenient way to like really trick this up without having to do all that stuff, let me know. I would sure like to know. So I have two different reactants. So again, I must find the limiting reactant. So again, I'm going to do the same thing, and I'm going to find their moles, their numbers of moles, and then I'm going to divide them both by their coefficients. And then I will find two different values. The lesser value is my limiting reactant, which is going to be nitrogen. This is the one I'll use. So then I'll take this part right here and do it again. And I'll take 4.4 times 10 to the 5th and divide by the molar mass, apply the mole ratio into the ammonia, and then multiply by the molar mass of ammonia to find my theoretical yield of 4.857 times 10 to the 5th grams, or 485.7 kilograms. Well, I produced 220. So I don't get a very good yield. You see how that works. I get 220 kilograms over 485.7 kilograms. And I get 45% yield. That's not that great. We will look at it in equilibrium to figure out how you can make things more efficient, because that's actually the job of chemical engineers. This is actually an equilibrium reaction, and there's things you can do to produce more ammonia and make this more efficient. So that's going to be it for me, guys. I want y'all to have a great day.